Yeah. Yeah. Hello.
Hello.
How's it going?
Good.
Good.
So exactly when problems due? Because I know.
Next Monday.
Okay. Okay.
I think, did we say that or did we say Wednesday? And I can't remember. Let's
Yeah.
wait for everybody to be on and I'll remember if it was Monday or Wednesday.
Okay.
Okay. All right, everybody, we should probably start. So remind me, guys, I'm pretty sure that we said we would give you like a little more than a week for the problems. So does that mean we're doing it Wednesday? Not, when did I give them out? I gave them out on Friday, right?
Yeah.
Don't remind me. I can't remember now. I can go look at my email.
I think I got mine on Friday,
Yeah, that's right. So it's Friday.
but
Okay,
so
I'm
sorry.
looking at my
So
notes to see when you said we were going to present.
yeah, I'm
We just
assuming it
only
would be
got them.
Monday after next Friday, right?
Whoa. What? Monday after.
Yeah, so not not obviously not today, right? Um, and not the 17th. I thought we would give you an extra time.
Yeah, I've
So
got
Monday
here
the
that we would have
20th.
gotten them on.
Yeah, Monday the 20th.
Okay.
Yeah,
Okay.
and I'll remember that. I'll try to remember that. Yeah, put that on Moodle.
And then, did we ever have extra credit problems?
I haven't put those up yet. I will do
I was
that.
just wondering if we were still going to do that or not.
Yeah, Yeah, I'll put
Okay.
those, I'll try to put those up sometime this week.
Sounds good.
Yeah, sorry.
Would those also be due on Monday, or would
No,
they be due
those are due
another
at the
day?
end of the class, end of the class.
Okay.
That make sense?
Yep.
Cool. Okay. So let me share my screen. All right. Okay. So we were talking about the free particle, right? And we were talking about how when we wrote down a solution for the free particle, right, that one, it looked a lot like a wave, like a traveling wave, right? So the free particle, and we had one looks like a traveling wave. I don't know if there's two L's in traveling or not. Okay. Traveling wave. And two, that it was not normalizable. Do you remember those two things, guys?
Yes.
Vaguely? Okay. All right. And so what we said was, okay, so we had the solution that, let me see, where is it? That looked like this. So basically the solution looked like a traveling wave. So it looked like phi of x and t is equal to a e to the I kx minus h bar k squared over 2mt, okay? And we said that, and recall that k, let me just write down what k is here. K is equal to plus or minus square root of 2m e over h bar, okay? And we said that if k, I don't know if we explicitly said this, but if k is greater than 0, right, we travel to the right. Travel to the right. I know that my writing is really bad today. I'm not sure why I'm not able to write today. And k less than 0, we're traveling to the left. Okay. And so we talked about a little bit about how this is a traveling wave, right? And it's called a plane wave. Okay, plane wave. And it's kind of like basically just a sinusoidal wave. So if you think of a wave, just a sine wave traveling down, right? Traveling in this direction. Okay. And that it's not normalizable because if you try to stick this psi into the integral psi star psi, you would put a e to the minus kx for this. So we'd have a star, right? A might be complex. E to the minus I, and then the stuff, right? This stuff. And then you'd have a e to the plus I stuff, right? Because that would just be the psi dx. And this would give you the integral. I can pull the a star a out and put that as just a squared like this. And this would be the integral dx. And of course, this is going over all space, right? Minus infinity to infinity. And so this is a squared. And then of course, this would just be x between minus infinity and infinity. And that would just give us infinity, right? So not normalizable. It's not going to be 1, right? It's kind of nothing we can do about that, right? That function is not normalizable. So what that means in the physical world. In quantum mechanics, right, we're trying to model the actual physical world. So what it means is that this thing here cannot represent a particle. Okay. Now, like I said before, in like 251, you guys probably talked about the fact that particles are waves and particles, right? And you might think, well, look, this is a wave, and that's what they were talking about, but it's not actually. Okay, so we're gonna get, we got there before, but I'm rolling back a little. So what can be done? This thing is not, this can't work, okay? Because it's not normalizable, it can't actually physically represent anything in the real physical world, because the probabilities, which is this thing, are infinite, which makes no sense. Okay. So what can we do? Well, what we can do is we can think about that the general solution, right? If we, in all the cases we've seen so far, was this linear combination of solutions, right? So that's the most general solution, like in the, right? So like we're thinking about the ISW, right? The infinite square well. We know that the most general solution for psi, and this really should be a capital. I don't know why I'm not putting capitals on everything. The most general solution for psi of x and t is this linear combination of all of the solutions to the TISE for the infinite square well. So this is n equal 1 to infinity. And then we'd have the CNs, and we'd have the psi n's of x, and the e to the minus I e n t over h bar, right? And just to write that out for the infinite square well, we get the square root of 2 over a. We'd get the sum n equal 1 to infinity. We'd get Cn. We'd get sine of n pi x over a, right? E to the minus En, and E would be the ENs would be the energies for the infinite square well, but it's too long to put in the exponent. But okay, so the solution is this linear combination with some coefficients, right? That are found because you know, let's say you know how the state starts at t equals 0. If you know that, you can find the CNs, and then you're good. You've got psi of x and t for all time. Okay. That's how it works in the other solutions, right? So for when the particle wasn't free. So maybe this is what will work. Maybe if we use something like this, this will save us from the problem that so far the solution to the TISE does not work for a real particle. Okay, well, we talked about it before, but really we just need to translate this whole thing into the case where we don't really have any integers. So remember where this n came from, right? It actually came from a boundary condition, right? It came from the fact that psi for the infinite square well had to be 0 at the boundaries, right, of the box, right? So once we implemented that boundary condition is when we got that n has to be like 1, 2, 3, 4, 5, can't be 1.25, 1.3, has to be integer. That's where we got that. But up here, we don't really have anything like that. We don't really even have a boundary condition except for psi has to be continuous, but kind of already looks continuous. There's nothing really to do about that. There's nothing that's going to make anything up here an integer. So we know k up here, maybe k would have been an integer or something, right? Which it was here. We started with a k over there in this case too. But there's nothing to force k over here to be an integer. So k is just this continuous number. So we need to translate from here, right, where we have a sum of these discrete things, to here where we have these continuous things. And that means we need to use an integral. So for the free particle, right, we're going to do this. We're going to do an integral. We're going to say that this is the integral of from minus infinity to infinity. And now we're not going to sum over n, right? But we're going to sum over its equivalent thing up here, which is kind of like k, right? We're gonna integrate over k. So this is going to be dk. Okay, that's kind of like the sum over n. It's the equivalent. And then we need something like the CNs, right? These are kind of the amplitudes. Remember we were talking about adding sine waves together? These CNs are kind of like the amplitudes for all the different sine waves. Similar thing here, we need an amplitude, but it's not going to be Cn. It's going to be a function of k. So we call that phi of k. And that dk, of course, that's for the whole thing here. I just wrote it first, so don't be confused by that, right? And then we need our size, which is up here, right? We need these guys. Okay, so I'm going to write e to the I kx minus h bar k squared over 2m t. And there we go, right? Now we also multiply by 1 over square root of 2 pi, and I'll show you the y in a second. But this is the equivalent of this, okay? It's taking all the functions, the solutions to the TISC, it's summing them, right, which is what an integral does, with amplitude, an amplitude function that tells you for every k, how much of each one of those to add. Just like this one, for every n, the Cn says how much of psi, you know, C2 is how much of psi 2 do you add in the mix, okay? Psi k is just continuous though, right? So when k is 1.2567, it knows phi of that number would be how much of that particular, you know, psi to add in to this whole mix. So it's really very equivalent. And it turns out, and I should have written, hold on, let me move out of the way here so I can write down, this is psi, so free particle. Okay, so it turns out that this solves the problem, okay? So now, if you wanted to normalize, so when you normalize, and I'm going to call this thing up here psi k, because it depends on k. And here, notice there'll be no k left, right? It's all integrated out. Okay, so we normalize psi of x and t, we can, so sorry, I'll just say it works. It works if we choose the right phi of k. Okay, so if we choose the right one of these, we can normalize our function. And if we can normalize our function, then this must be the right one for a free particle. So a free particle isn't just one wave, because we can think of this as actually an addition of many waves, right? Because each one with a different amplitude. So it's not just one wave, like a sine wave, just one sine wave going down the road. It's what's called a wave packet. So a packet of waves, similar to what you do when you mix sine waves to get a particular sound, right? We saw that in our simulation. So this is called a wave packet. And this is what they were talking about in 251 when they talked about a particle being a wave and a particle. They were talking about the wave part of it is this wave packet, okay? It's this mixture of a bunch of different waves together to make a whole new wave, okay? Does that make sense? Let me get the simulation up for a second and I'll show you. Let me just, sorry, I should have gotten it up before, but I forgot to. Oh, just a minute. Sorry, I've got a Mac problem over here. Just a minute. No. I hate this. It drives me nuts. Come on. Just a second, and then I gotta change the screen share so you can see this. Okay, so you can see the simulation. We saw this before, right? So I'm gonna go over here to discrete to continuous, and I wanna show you something. This is kind of a discrete version of this integral that we were just looking at, right? This thing down here. Oh, you can't see it right now, never mind. You can look at your notes for that. But if you look, all these waves, there's a bunch of waves that all the components are being added together here. These are all the component waves. So I think if I click, now I wish they would let you see which one is which. But what's happening here is that these are the amplitudes, okay? So for a wave with a K of 4 pi, right? The amplitude is tiny. When the K is 12 pi, right? It's big. So this Gaussian function, you can kind of see this is a Gaussian function. This is the equivalent of, and I wish, hold on a sec, I think I can write on this. Let me see. Yeah, I might be able to add it on this. We'll see if it works. Sometimes it doesn't work. This thing here is the equivalent of the phi of k, right? So this function. So now if I think of this now as continuous function, that would be the equivalent of the phi of k, right? So this would be, phi of k here, right? So it gets big when k is near 12 pi, and then it drops off as k goes out and becomes much bigger, and drops off as k goes to 0, okay? So this is the equivalent of the phi of k, and then these are all the waves that are being added together, okay? This says sine, but remember when we have something like e to the, I something, I theta, that's the sine and the cosine, so it's really the same thing. So it's adding a bunch of sine waves, and our equation is also doing the same thing, adding a bunch of sine waves equivalently. So if you notice, there's a bunch of waves here, and these are all added together to make this thing. So this is all the components all stuck right on top of each other. They're not added together yet, but when you add them, you get this, okay? So think of that as kind of the free particle wave packet. That's what it looks like for this particular case, where phi is this, kind of Gaussian looking bell-shaped curve, and you mix all these guys together, you get this. And now imagine that traveling, down the road like this, right? That's the wave packet. That's what represents, say, the electron, okay? And so this is what we call the wave packet. Okay, and this is what they mean by wave particle duality, right? Particle wave. Okay, is that sort of clear on that? All right, let me do a little bit more math, and we'll come back to another simulation. Okay, so we said it can be normalized for suitable phi, and that's true. And we will see how that I'm gonna actually go through an example on this, but first I'm gonna write down that if, remember what we do for this case, right? We're always, for the case where we have this discrete sum, and what we usually have is some idea of what's going on at t equals 0. So we know psi at t equals 0. And then we go through and we solve for all the CNs. We've done that a few times, okay? And then we put together our psi of x and t. Well, a similar thing happens here, okay? So if we write down for psi of x and 0, I can write down exactly what it is because, or an expression for it here, I can say, well, it's 1 over square root of 2 pi, the integral from minus infinity to infinity, phi of k, and then e to the ikx, no t because the t is 0, dk, right? That's what that is. This is what psi at x and 0 is. And now if I know what this is, let's say someone tells me that psi at x and 0 is 2, right? Then I can find the phi of k in a similar way that I found the CNs before. Okay, and it's called Fourier's trick. I hope we remember that we called it Fourier's trick before. And that's because this integral here looks a whole lot like the inverse Fourier transform. So let's write down what I even mean by that. So I'm going to first write down the Fourier transform, and that's f of k. So, and this is called the Fourier transform. And that's equal to 1 over the square root of 2 pi, the integral from minus infinity to infinity, the f of x, I'm going to explain all this in a second, e to the minus I kx dx. And there's the inverse Fourier transform, which is f of x is equal to 1 over the square root of 2 pi, the integral minus infinity to infinity, f of k e to the ikx dk. Okay, so these two things, the Fourier transform and the inverse Fourier transform, are the expression of the continuous expression of adding waves. Okay, so if you think about here, let's say we have, this is an amplitude function, okay, and these are the waves you're adding. Similar thing here, but I want you to notice that f of k is in terms of the k's, which are kind of like wavelengths, wave number, and f of x is just in terms of space, like x, right? So if we look here, you can see that this integral looks a whole lot like this integral, except for this thing is phi of k, right, instead of f of k. And this thing is psi of x and 0 instead of f of x, okay? So this looks a whole lot like an inverse Fourier transform. So if I want to get this, because remember that's our phi of k, I need to do this integral over here, okay? So I need to take my psi of x and 0 and stick it here and multiply by my e to the minus ikx and integrate over dx, and I'll get my f of k, right? I'll get my phi of k. So what I can do is I can write down phi of k is equal to 1 over the square root of 2 pi, and then the integral minus infinity to infinity, and then psi of x and 0. Remember, someone might tell us it's, psi of x and 0 is 2, so you put 2 there, and then you'd integrate, you put multiply it by e to the minus kx, and then you'd integrate over x, and you'd come out with the phi of k. Okay. All right. I need to do a new layer. Do you need a little time to write this down, guys? Hello?
Oh, I'm good.
Okay.
I got it.
All right. Let me get a new layer. Okay. Let's do an example. Okay. So we have, let's say we have a free particle And someone tells us that at t equals 0, the free particle is, you know, some constant, A. And it's only A if x is between minus little a, sorry. So it's only A for some region, right? So if we drew it, it would be like, okay, psi of x and 0, sorry. And there would be like x equal A and x equal minus A. And psi of x and 0 would just look like this. And then it's 0 otherwise. Okay. So that is the psi of x and 0, okay? And so they told us that's what that is. So now I want to know, what is psi of x and t? In other words, what is it for all time? Okay, well, to do that, right, I need to find the phi of k's, because I know that the psi of x and t is this. The integral minus infinity to infinity of phi of k e to the minus I, e to the plus I kx plus h bar, I can't remember now what it is. Is it h bar squared? I'll go back and look. No, just h bar k squared over 2m t dk, right? I know that's the case. So if I found this, I could at least write down an integral equation for what psi of x and t is. Okay. So I need to find this, but we were told how to do that. So remember, I just wrote down, I'll just write it again, that phi of k is this integral, right? And we put psi of x and 0 in here. We multiply by e to the minus I kx, and we integrate over all the dx from minus infinity to infinity. Okay, well, let's do it. We know what psi of x and 0 is. That's easy. Okay, so let's write it down. So we have 1 over the square root of 2 pi, and we have minus infinity to infinity, and then we have, excuse me, a, I'm just going to put a in here, right? And then I have e to the minus I kx. Okay, well, I don't have to integrate from minus infinity to infinity, because look at what psi of x and 0 is, right? It's only non-zero between minus a and a. So I should have just written down that this is minus a and this is a, right? Because outside of that, it's 0. So I don't have to deal with that. Okay. All right. One thing we probably should do is think about, can we normalize psi of x and 0, right? But we'll deal with that in a second. Let's just keep going with the integral. Okay. So here, right, this integral here just becomes a very simple integral, actually. It's a over the square root of 2 pi. And then it's the integral e to the minus I kx dx minus a to a, right? So, all right. So that's a pretty easy integral to do, right? We can say, oh, let's let u equal minus I kx du is minus I k dx. And so we'll put a 1 over minus I k out in front. Then we have the a over the square root of 2 pi. And then we have the integral of u du. Sorry, no, the integral of e to the u du. Sorry. My pencil just got stuck over here. Just a second. What are you doing? Just a sec, my pen's stuck. I gotta figure out why it's stuck here. There we go. All right. Okay, it's e to the u du. And of course, the integral of e to the u du is just e to the u. Okay, so I'll substitute back in. So we have 1 over minus I k a over square root of 2 pi. And then we have e to the minus I k x from minus a to a. Okay, so we'll keep going here. 1 over minus I k, and then a over the square root of 2 pi, and then e, let's see, to the minus I ka minus e to the plus I ka. Yeah, so far so good. And let's, I'm gonna bring this minus sign out and just like put it over here. So I'm gonna go, okay. So let me think, yeah, okay. So we're going to pull the minus sign in and pull the I and the k over there as well. All right, so we're gonna have a over the square root of 2 pi. And then we're going to have e to the I ka minus e to the minus I ka over k. All right. Well, let's just look at this thing right here. This quantity e to the I ka minus e to the minus I ka. So e to the I ka minus e to the minus I ka. All right, this right here is the, remember how this is the cosine of Ka plus I times the sine of Ka. This thing here is with a minus sign, so we have minus cosine of Ka minus I sine of Ka. And notice what happens with my minus signs here. I'm going to cancel my cosine terms, and I'm just going to end up with 2I sine of Ka. So that's in fact what this is here. And I'm going to leave the K there, right? So basically, we're just going to replace this. So we have A, oh, I forgot my I, sorry, I. Over the square root of 2 pi, and then we have 2I times the sine of Ka over Ik, and the i's cancel, and I'm left with A times 2 over square root of 2 pi sine of Ka over K. Okay, so that's what phi of k is. It's this function sine of x over x, basically, or sine ka over k. What we didn't do is we didn't normalize. So remember that if you have psi of x in 0 and it looks like it's normalizable, and in this case it actually does look normalizable because it just goes between minus a and a, then you should probably try to normalize, right? And that will help us because it'll tell us what big A is. So we didn't really do that. Well, let's do it now. We can just take this guy and do psi star integral psi star psi. So the integral psi of x and 0 star psi of x and 0 dx, set that equal to 1, and that's going to go from minus a to a. Well, that's just this thing right here is just a squared. So we just get a squared, and then we have the integral dx from minus a to a, and that's just going to be a squared, and then we're going to get a minus a minus a, so plus a. And so that gives us just 2a squared is equal to 1, which gives me that a is equal to 1 over the square root of 2a. Okay, so that's nice. So I don't have to carry that big A around. So I'm going to write down now my thing for 5k, right? This whole thing here is to 5k is 1 over the square root of 2a square root of 2 pi. And that's with 2 on the top. We'll cancel those 2's in a second. Sine of ka over k. And let me move my little thing here so I can continue writing a little bit. Okay. So I'll get rid of the 2. See the 2 here cancels with these two 2's. So we get 1 over the square root of pi a sine k a over k. This is the function that hopefully will allow this big psi of x and t up here, right, to be normalized. Okay. So let me write down that big psi in a second. Let's see, did I write that down here? Yeah. All right. So I'm going to get a new layer. Can I get a new layer? Okay. I see one thumbs up. All right.
I'm
Can always
good.
go. Okay.
Yep.
Great. Okay. So now that we found 5k, we've got it. We've got our whole psi of x and t. It's 1 over the square root of 2, I need the square root out of the way. Remember there was another square root of 2 pi in front of the psi of x and t, so we're gonna conglomerate those constants. So we have pi times the square root of 2a, and then the integral minus infinity to infinity, and then 5k, which is sine of ka over k, and I already pulled the constants out that were over here. And then e to the I kx minus h bar k squared over 2mt dk. This is psi of x and t. Now, yeah, I can't actually do that integral, right? You can't actually do it. You can do it numerically, but this still tells you what does psi look like for all time, okay? And let's take a look in more detail at that particular solution. Okay, we can look at some limiting cases to see if this, makes sense quantum mechanically for this to be the case. Okay, so let's take a look at a limiting case. Okay, look at A small. So remember what A was, right? A was that region in which the initial wave function existed, right? So if we have minus A here, right? Then we had that, this thing was, now we know that's 1 over the square root of 2a, right? That constant value. This was psi of x at 0, right? So if A is little, that means it's combined, that from that initial wave function is confined to this really tiny little space, okay? All right, so what if that's the case? Well, let's, the limiting case, A small. Well, this would tell us something about sine Ka, right? Sine of Ka, if A is small, right, this is approximately Ka. We should remember that, right? Sine of theta is approximately theta when theta is little, right? Okay, and so phi of k, and I should write, let's go back to here for a second so I can just look at my phi of k. Down here, it's 1 over the square root of pi a, right? Go back to here. So let's write that down somewhere. It's up here, but I just wanted the constants are 1 over the square root of pi a sine ka over k. Okay. So phi of k up here, right, is going to be 1 over the square root of pi a, and then approximately, right, ka over k, right? And the k's cancel, and so we get, and the a's, I'll bring the a into the square root, and so we just get square root a over pi, right? When a is small. Okay, so if we think about it, psi of x and 0, right, now is this really narrow thing, and I'm gonna, in the limiting case, psi of x and 0, I'm gonna draw it differently now. It's this really, teeny little spike thing, right? This is psi of x and 0. Right, because this is a over here, and this is minus a. So it's a really well-defined position, think of it that way, right? Because if I want to know where is the particle at t equals 0, it's easy for me to tell because a is so small. I know it's, let's say a is a nanometer, right? That the particle is confined to be within a nanometer. I'm pretty good at figuring out where it is then, right? Okay, but if you think about phi of k, when we look at what phi of k looks like, phi of k is just this constant, square root of a over 2 over pi. Right? It's just a constant. It's like just the line forever, right? And so it's very spread out. All right, so now what we're seeing here is that this is kind of like, the position, right? This is the position because it's psi of x and 0. This is more like the momentum. Okay, so when you have a very, very, very well-defined position, you don't have a well-defined momentum, right? Because if you think about what is the probability here, right, what we do, we would square psi, right, psi star psi. And that would just give us, a squared. That's little, even when a is tiny, right? Phi star phi actually would be the probability of finding up the momentum of the particle, and that's just going to be a over pi, right? That's a constant, right? So this is kind of like the momentum distribution, and this is kind of like the position distribution. Does that make sense? Yes? Okay. So when you've narrowly restricted the particle to a narrow region, your now momentum is everywhere, right? Okay. Let's look at another limiting case, a big. Okay, in this case, right, a is really, really big, and the particle, let's say, is, in a box that's, a meter long, big, right? Really hard to tell where it is. Okay. So it starts off in this region where a meter wide or something, some big A. Okay, so if A is big, right, we can look at the function phi of k again. Let's look at phi of k. Remember that's the square root of a over pi. I'm writing it slightly different, by the way, for a reason. So sine of ka over ka. So what I did is I multiplied and divided by a, so I could have a ka on the bottom too. That's what I did here. Okay, so at 0, right? So we're gonna have to figure out, what does this even look like, this sine of ka over ka. So what happens at k equals 0? So at k equals 0, so we're trying to plot this, is what we're doing right now. At k equals 0, what happens? Well, we know that by the, this would be 0 down here, right? K would be 0 on the denominator and 0 here. But if you hopefully remember that the limit of this thing, right, is 1, right? If you don't remember that, that's one of those things you had to use L'Hopital's rule to calculate back in calculus. Okay, so at k equals 0, we have 1. This sine k is 1, so we get phi of k is just square root of a over pi, right? K equals 0. And then where does it go to 0? Where it goes to 0, right? The sine ka over k goes to 0 when ka is equal to pi, right? Because that's, well, pi or minus pi, plus or minus pi, and multiples of that. Yeah? So if we draw a plot here for phi of k, it's a maximum here at 0. So this is k. Sorry, this is k. This is phi of k. And it goes to 0 at, say, you know, k equal pi over a, right? According to this. And minus pi over a. So it does something like this. Okay. And then, you know, it goes off and does other things. It comes back to 0, et cetera, right? Okay. Now, if a is large, then pi over a is small. So this actually, I've drawn it pretty big, but it's really this sort of very narrowly peaked thing, right? Because pi over a is so little that, like, right, it's this narrowly peaked curve thing, right? But what about the position? What about psi of x and 0? Well, we said a was big, right? So that means that if I draw psi of x and 0, right? This is psi of x and 0. And this is x. This is just going to be really wide, right? So say a is like 10,000 and minus 10,000, so it just keeps going. So again, this is the same idea where you have a very, but now we're switched, right? Your particle is, you know, the probability of finding it is, you know, the same everywhere, and you can't really tell where it is, but your momentum is very strongly peaked, right? So that's easy to predict what the momentum is, but not so easy to predict where the particle is. So it's that uncertainty principle once again, because this, of course, represents the position distribution, and this represents the momentum distribution. Okay, so those are our two limiting cases that sort of show you the position and how position and momentum really stand up, right, against the uncertainty principle. And let me just point out that, let me go back to my other notes just a sec.
Hey, Shank,
Yeah.
can you let Zoe back in? She got kicked.
Oh no, what happened?
I don't know.
I just saw people coming in from my other class, so. All right, so let me point out that, remember that the momentum, so why am I calling this a momentum really? It's because the momentum, like if you think about in 251, the momentum is proportional to k, or say a photon, h bar k, right? I remember that. So the k really is sort of a measure of momentum in quantum mechanics. Okay, so this is kind of the momentum distribution, and this is kind of the position distribution. Oh, I just let her in, but it just kicked her out again. Okay, well, class is over, and I'll put something on Moodle to say that we're doing Wednesday, right? Okay, Wednesday. All right. Okay, guys. See you. I gotta let people in for the next class.
See you Wednesday.
See you.
You're muted, Shank.